सामने आओ ना यार एक बंदा. Welcome everyone to this webinar on AM PravaH, world's first all-inclusive 3D computational software for additive manufacturing. And last time we left off with the presentation or a webinar on laser 3D printing multi-scale modeling. This was almost 8 months ago, and we were able to indicate and show different results catering to 3D printing industry at different scales such as micro scale, meso scale, and macro scale, and also some particle modeling as well. Now going on to the 3D printing processes and what exactly we want to accomplish with AM PravaH is improved economics due to early defect prediction, yield improvement, cycle time improvement, waste reduction, process knowledge and innovation. And the way AM PravaH tries to address some of these issues or majority of these issues is dividing the whole modeling regime in two parts. One is pure physics based modeling and another one is pure database modeling. Now when we talk about physics based modeling, we are talking at a part scale where we want to do FEA and thermomechanical analysis of the part, of the entire part. At the macro scale modeling, we want to perform the continuum scale modeling that involves melt pool dynamics and laser dynamics, particle dynamics, things like that. And then at the macro scale level, we want to capture the grain size, orientation, misorientation, and more of a Monte Carlo simulation side of things. Now all this is fine for people who are into computational and experimental modeling front, but then additive manufacturing being a relatively hot field of research, a lot of new data is also generated basically every day by researchers around the globe, and we have included an artificial intelligence module as well to this AM PravaH, which is quite advanced deep learning based module that allows the users to basically make use of the existing data and also the new data that will be generated either through computational modeling or through experimental modeling. And we will see some of the examples of how we can use these two models in sync to attain the best designs and builds from additive manufacturing processes. Right. So first let's focus on the physics based modeling, which is macro scale and micro scale. Just a quick note that we are also working on the part scale FEA modeling. We have everything ready. It's just a matter of time before we will start shipping the thermomechanical model as well with our software. Right? When we talk about physics, it's not like traditional aerodynamics or external aerodynamics type of problems where you are focused on a certain physics in great depth. When we talk about additive manufacturing, you are talking about multiple phases. You're just not limited by one or two phases. You can actually have multiple phases such as the solid substrate, the molten substrate, the vapor, the inert gas, and then you have phase change happening between all these phases, thermodynamics, surface tension, laser dynamics, and particle tracking for powder distribution, especially with LPBF type of processes, right? And on the micro scale front, you are very much interested in grain growth, grain misorientation of an alloy once the laser has run over the alloy and it is going through the solidification phase. And this micro scale modeling can have direct impact on the properties such as creep and strength of an alloy. Right? So we strongly believe in dedicated and a dedicated verification and validation manual for all the work that we do, and we have done the same for AM PravaH as well. And I'm going to go through some of the validation cases over the next few slides just to give you more just to build more trust and convince you that in fact we have not put together any random solvers in this software. They are quite state of the art, and as I speak, more and more development work is going behind them. So this is a simple case study of laser beam welding, one of the simplest validations I am going to show today, AISI SS304, and we had some results with in comparison to another commercial software as well. So that software does not come close to the experimental data. So I mean, there was no point putting the results here anyways. We are comparing it our data directly with the experimental data, right? And for different combinations of laser power and welding speed, so there are 4 such combinations. We have some data available, the experimental data available for the depth of penetration and the weld width, and we took that experimental data and we simulated the same set of parameters in AM PravaH, and we compared the results. You can see that for the depth of penetration, the error is under 4% in the worst case. The error varies from 0.5% to around 4%. And if you go to the weld width error percentage, the error percentage is actually under 1%. And based on the amount of sheer amount of physics and numerical techniques deployed, I mean, this is quite good, excellent results, I would say. Moving on to a complicated case of LPBF, laser powder bed fusion for Ti64, a common alloy. And here also the situation is similar. You know, we have 4 different combinations of laser powers and scan speeds, and they are trying to report the width of the weld pool compared to experiment and the comparison with the experiment. Even here the error percentage is reported under 4% or 3.5% at the maximum, and 1.7% the lowest error possible. So yet again, this is an excellent validation. Moving on to the microstructural side of things, what we have is the validation case study involves grain structure prediction of electron beam welding for nickel 200 plates, and we have 2 images on the right hand side of this slide. On the top the top image is a cross section that is cut through the weld pool, and the bottom image is actually the laser scan track that we see from top, right? And you can see that the right hand side experimental results match very well to the grain size distribution that is predicted by AM PravaH's Monte Carlo simulator. And then on the bottom side, if you look at the laser scan track, the results compare very well again to AM PravaH's Monte Carlo simulator. And if we talk about experiment and simulation results, I mean, visually it's all good, but if you were to compare quantitatively compare the experimental data with simulation data, you can see that the ECD, which is effective circular diameter, so what they have done, they converted the circumference of a single grain into a circle, so that they have some relatively same parameter to compare against. And the fraction of grains, so for example, ECD of 1, you can see experiment and simulation have a very similar fraction of grains for an ECD of 1. There are some variations, but nevertheless I would say that these are quite promising values given the challenging nature of such simulations, right? Another one we have is the grain structure evolution in LPBF of Ti64, and in this case we are interested in the misorientation or the angles of each grains. So if you go on the very right hand side, the plots, you can see that the fraction of grains versus simulated angle from the normal, and then on the bottom if you see fraction of grains and again angle from normal for experimental results. The results are quite similar to each other. In fact, if you look at this in a visual manner, if you look at the transverse view, you will see that the scan, based on the scan direction, it is hitting into the screen. The laser is hitting into the screen. You can see that large columnar grains are predicted by both simulation and experiment. Some center line axle grains are predicted by both simulation and experiment, and the same similarly fine curved and columnar grains are also predicted in a very good way. If we move on to the top view, and then the scan direction is going up and down on this screen, not into the screen, again you can see large columnar grains, central action grains, and fine and curved columnar grains, very similar to some of the experimental photo. So the experimental one is the left one in both the cases, and simulation is on the right one in both the cases. So moving on from the validations, let's focus a little bit on laser powder bed fusion, which is at the core of AM PravaH software. Uh, and I mean, the process involves putting laying down a powder bed with a certain size of particles, and the particle sizes, they don't have to be constant either. They can be a Gaussian distribution or some sort of distribution such that you get the maximum packing with the particles. And then you hit a laser on top of this particles, which is on top of a substrate, and then those particles melt, and basically they merge together with the underlying layer or the underlying substrate. Right, so there are two processes here. First one is powder spreading, and the second one is LPBF, which is the actual CFD modeling, or the actual actual fluid mechanics, thermodynamics, and laser dynamics that is captured on the right hand side of the image. So in AM PravaH, we have tried to capture both of them very accurately. So for the powder spreading part, we are using an exact DM simulator, and for the right hand side, we are using the exact CFD simulator. A quick note on the physics of such processes. I mean, again, you have a melt pool, you have a laser beam hitting the melt pool, you can have laser reflections and thermal fluidic convection, surface deformations, you have Marangoni effects, particle dynamics, solid state transformation, and solid mechanics as well. And overall, this is quite a complicated process, and we have tried to capture as much as possible without taking a huge toll on the computational power. A quick comparison of how the results that come out of AM PravaH look like. So we have taken 3 different alloys for the same set of process parameters. So these are all commonly available alloys, but you don't have to stick to them. You can work with any alloy of your choice. And we have also provided a database of alloys, which I will be showing very soon in a live demo, where I'll open the software and run you through the different buttons and the design of the software. But anyways, SS316L, Inconel 718, and Ti 64. Okay, very well known alloys, and they have very different thermophysical properties, varying all the way from different molecular weights to melting temperatures to viscosities, density, surface tension. And then of course it is expected that the solidified build that you will get out of these 3 alloys are going to be quite different, even with the same set of laser properties. Right, so the power that we are using is 280 watts with a distribution type Gaussian, focal radius of 0.15 millimeter, and we have Fresnel refractions. Fresnel refractions and scattering is turned off to keep things simple for now. And the powder bed, this is what I was talking about. It is a Gaussian distribution, so you don't have a constant particle size powder particles. You have basically a distribution going from 60 microns to 80 microns, and then the maximum of the particles are somewhere in between, as usual with this bell curve sort of distributions at 70 micron. We are going to do two layers, basically approximately 2 layers of particles per powder spreading. Okay, if I show the video, this has come out of AM PravaH. Okay. I'll play it one more time. Okay. The scanning strategy, there are many scanning strategies such as stripes, islands, rotation, nested strategy, but we are going to go with the most commonly used stripes strategy. We will have 1 layer, but the number of tracks are going to be 4 with a hatch spacing of 0.4 millimeter and a scan speed of 1 meter per second. We will be considering 3 phases here, and please note that as I mentioned earlier, we can do any number of phases which might be relevant to your problem, but in this case we will be doing solid phase, which represents your actual solid alloy, the liquid phase, which represents your molten alloy, and the inert gas, which is a chamber in which all this activity is going on. Okay. So if you were to compare the results that came out of the simulation for these 3 alloys, you will see that the distribution or the temperature distributions are quite different for these 3 alloys. If I play one more time, yeah, the width of the streaks and then how much temperatures we see is quite different for all these three. But at the end of the whole thing, at the end of maybe good amount of solidification, you can see that the streaks or the final build comes out to be quite different. Now these images are not experimental or any X-ray images or nothing like that. These are actually just the post-processing images that AM PravaH is capable of producing. We have coupled a very or the state of the art post-processor available, which gives you capability to produce almost movie grade and photorealistic looking images and videos. We have used that in this case study as well. And you can see that SS316L, Inconel and Ti64, they have very different scan tracks after solidification. Right? Some other capabilities of the post processor: you can take clips across the laser, and you can take cross section, cutting through the melt pools. You can see that the cooling is happening from the bottom towards the top, which is expected. And then if we look at the cross section of the melt pools, and again these results are already quite good for the amount of computational power that is deployed. I mean, they're not run on any fancy computers, they don't take days to run, they are all parallelized. So on top of that, I mean, they give you results quite quickly. And then again, this is another ray tracing or photorealistic visualization that we have done using AM PravaH. You can see for SS316L, Inconel 718 and Ti64, the melt pools are quite different, which is expected. And if we were to summarize, there are some observations not very relevant for this webinar, but yet there are some observations regarding the shallowness of the melt pool or the narrowness of the melt pool, how much temperatures, how much each of these alloys actually heat up when the laser hits them, how much of overlapping is happening between the scan tracks, how far are the scan tracks spreading from their original position, how dynamic are the melt pools. So these are some of the observations that you could make right off the bat using this software, right? And like I said, this is not limited to one layer additive manufacturing processes. This is multi-layer. So we'll do layer 1, 2 scan tracks, and then we'll put, using DM, we'll put another layer, and then again we run 2 scan tracks. This is for layer 2. Okay. Moving on, this is the visualizer that we have. We have coupled ParaView in the background. I can tell you this is to the best of my knowledge the best post processor out there, and in fact some of the commercial companies are also moving to ParaView. They just changed the name of this software to something else, and basically it's ParaView in the background, and it gives you immense capabilities in terms of calculators, contours, glyphs, clips, slices, streamlines, integrating variables. There's an entire data analysis module. You can actually write your own Python code or extract all your activity in the form of a Python code. So it's very parametric in that sense, and the possibilities are basically immense with this visualizer, right? We have also done some work on wire direct energy deposition, DED process, and where we basically inject a wire and you hit the laser at the end of the wire just near the substrate. This wire melts and basically deposits over the substrate. If I were to show the video for this one, you see that the wire is coming down from a nozzle, and this is all happening in a very zoomed manner, and there's a laser that is hitting right at the intersection of this substrate and the wire. You can see as the substrate moves from left to right, it's carrying the wire away from it. Yeah. Okay. So like I mentioned earlier, within the macro scale modeling itself, there are a million things that are going on, and we have put our best effort to capture everything simultaneously, including laser dynamics, material properties, heat and mass transport, multi-phase physics, and then there are other miscellaneous modules possible as well, right? On the micro scale side of things, we are interested in grain distribution, where during melt pool solidification grain boundaries move around, they rearrange, they misorient from the supposed to be orientation, and the grain size increases or decreases based on the grain boundary area per unit volume, right? In a normal grain growth, this occurs relatively uniformly, but in abnormal grain growth, one grain grows at the expense of the other. So one grain will increase in size, the other grains will have to shrink, because I mean the volume has to be conserved, right? So what exactly we do in this sort of modeling using AM PravaH, we do I'm going to show 4 layers of laser scanning and corresponding changes in grain size distribution. You can see in the beginning all the grains are randomly oriented. So layer 1 is track 2, layer 2 track 1, track 2, and then layer 3 track 1, and then track 2. Then if we go to layer 4, we have track 1 and track 2. So at the end of this whole process, you can see the grains have completely misoriented, and we are able to capture different, we are able to visualize. Again, we have focused a lot on the visualizers, and not just on the solvers. And the idea is, if you can't create and use meaningful data, I mean there's no point of doing all these complicated simulations, right? So we have added a lot of code to be able to visualize the misorientation angles, and then able to visualize these grain orientations in different Euler angles as well, right? Okay, so on micro scale front, like I mentioned, I mean these things, I mean for those of you who are doing experimental work, they will understand and appreciate that some of these parameters that are dependent on grain size distribution can directly affect the strength, toughness, creep and fatigue of an alloy, right? And then moving on to the data-based modeling, before I'll show the live demo. The idea here is to improve the existing research and keep improving it as we use this deep learning modules in the future as well. So how can they help the current users or current experts in the AM industry? So this deep learning module or artificial intelligence module can help experimental and computational people both in real-time decision making to maintain the process efficiency. It can help in prediction of experimental outcomes based on previous experimentation, because experiments are expensive, simulations can be long to run, but yet so once you have a lot of this data available, or some amount of this data available, you can sort of have a virtual assistant that can keep helping you down the line with all the experience it has gained in the previous experimental or computational work. So one example could be a simple prediction of macro scale and micro scale parameters based on the process parameters and the operational parameters that you have put behind the machine, right? We have provided some default NIST data sets from National Institute of Standards with our software. So one case is where we show in the demo is, we take some user process and alloy properties, and based on that we'll predict what can be the melt pool width, depth of penetration, and more things like that. And those of you who are from this deep learning background, you will realize that this graph basically shows that as the AI module is learning from this data, the error is going down, which is a good sign, and it becomes kind of steady after let's say 10,000 iterations, right? So in addition to all this, we are going to include more AM processes such as binder jetting, and more DED based processes, fuse deposition modeling. I mean, we have the solvers in place for pretty much everything at this point. It's just a matter of deploying it into our user interface, which we have developed completely independently at our team at our office at Paanduv. And so the part scale modeling, which is our next high priority thing in terms of thermomechanical modeling. Dendrites modeling, we are still to validate some of the results on that front. A lot of request is coming for image recognition based AI for experimental photographs that are generated by the researchers. I mean, much of the data is collected in the form of images and X-rays and some infrared images, and that they can directly be used to understand what is the fate of this build, and you can improve your processes accordingly in real time perhaps. right? And then more material characterization possibilities. I mean, we are doing some of that with this Monte Carlo simulation, but we look for a dedicated material characterization modules as well in our AM PravaH. Okay. So let's stop this presentation for a few minutes and actually go to the demo of our software. So like any other software, we just click on AM PravaH and a terminal will launch. Okay, and along with it, an user interface will open up. Now please note that this terminal is intentionally kept decoupled from the interface for the maximum performance issue. So we are almost borderline obsessed with the performance of all our computational models, and we really want to keep our interfaces lightweight so that when you are running simulations it does not kill other processes and slow down your computer. So I mean, very flat and I would say modern design, and very user friendly as well. We have not put a million buttons at the hands of the users because many of the additive manufacturing folks do not come from that background of hardcore computational modeling, right? So if we have to we can give some name, for example, live demo webinar, create new, just put it in document somewhere, click OK, and you'll notice that everything that we are doing, it will keep reflecting on the terminal on the left hand side, right? So the first window is of course macro scale modeling, where we have divided the screen in three major parts, and the first one is properties section, the second one is computational settings section, and the third one is all the buttons that we want to that basically help us in taking actions, right? So if you focus on the first one, which is the properties section, we have a lot of features available for providing the properties of an alloy, and then we have also loaded up some of the default alloys. So we can load up, for example, Ti 64, Haste alloy X. You can see all the things that you're doing in the user interface is reflected in the terminal immediately. And as I'm changing these alloy default alloys, I am also changing the properties for the solid and the molten alloy. Both are automatically updated, right? But you don't have to use any of these alloys. You can use whatever alloy of your choice. So if you know the values of your alloy, you can use them, and if you don't know all the values for your alloy, you can leave the remaining values at default, and after some calibration you will be able to get the alloy of your choice. Again, I mean, we have inert gases, mostly it's argon or air, and the same, just like alloy, you can have your own inert gas available as well, right? You can just hit save and everything will go back to usual, right? And we hit save, go back. Then let's look at process parameters. I think this is very carefully built. First section is laser properties, second section is powder spreading. In the laser properties, first of all, the very first thing we do, we upload a scan pattern. Okay, we upload a scan pattern, and let me upload this pattern, and I'll also show what is the amount of flexibility that we are talking about here. So this scan pattern is basically any Excel file or a CSV file which contains the layer number that you are in, and then it contains the time and the XYZ coordinates of a laser, right? So basically you can define n number of layers, and each of these layers you can have a different scan pattern altogether, right? You can decide the angle at which laser is hitting in this X, Y, and Z direction, laser beam radius, laser power. These lasers are not actually uniform in nature, so they have all their heat sources are Gaussian, there's some Gaussian distribution to them. Laser efficiencies, they are not 100% efficient. And very important thing is initial chamber conditions. So you have temperature, you have pressure and substrate height, and you can basically provide this. You can start off with sort of a preheated metal, and these things are possible, right? Then you provide number of scan layers. This is a redundant variable because based on what you have provided in your upload scan pattern, it will automatically understand how many layers you have, and so you don't have to actually provide a number here. Another very cool thing is uploading custom powder distribution. Okay, so you can have in this, you can again have an Excel sheet or a CSV file where you just have to mention the size of the particles and the percentage of the particles, and then go to the next row, size of the particle, percentage of the particles. Very straightforward there. Then we have spreader clearance from the particle bed. So what is the distance between any current layer of your build and the spreader height for spreading new layer of powder. Velocity of the spreader, and I mean we have exposed quite a few details here. Not really necessary to change any of this, but there is an option. So we hit save, okay, and it's saying no such file because we have not loaded any file really here. So we'll do scan pattern for CSV, we'll do powder for this, okay, hit save, and then we go back. So this time it didn't give any error. So it will keep giving you errors as well if you do things that are basically logically incorrect, right? The next tab on the right hand side is the computational settings, and this tab is quite powerful simply because you can tweak around with the accuracy, performance, and data saving frequency. I mean, this looks very simple, but there's a lot of algorithm that goes behind setting these sliders. So for those of you who are from the computational field, you will know that accuracy and performance are typically inversely proportional. Okay, so if you are going for 100% accuracy and 100% performance, this means that the solver will give equal weightage to both accuracy and performance. But let's say if you go for 100% accuracy and 50% performance, the solver will automatically give twice the weightage to accuracy compared to performance, right? And this basically gives the user flexibility to control how much accuracy they seek from the simulation work, and balance it with the type of computational power he has available with him. Okay. Then we have data saving frequency. Again, this goes back to how much storage is possible on your computer, or even if you have a lot of storage, how much data do you really want to save while a simulation is running. And the last aspect is high performance computing, where the solver automatically picks the number of physical CPU cores you have. So my machine, for example, has 12 cores. If you want, you can change it to 4 cores or something like that. Okay, and then again you hit save. Okay, and yeah, you run the solver and hopefully it will run. So it's saying melt pool modeling is started, pre-processing, LPBF layer 1 is running, discrete element method is going on right now for powder spreading. So right now the powder is spreading, and then because we have, I think, one layer only in this demo, so this is how it goes. So we won't be able to showcase the real simulation run, but we have some of the results available that basically it's the same simulation that I showed in the presentation that we are using for the demo purposes. So actually we had 2 layers in our Excel file, so it will take 2 layers from there. Okay. So this is you can see that earlier I ran the simulation with 6 processors, so that is there. Okay. All right, so let's see. Yeah, one more thing, you don't have to really go anywhere to visualize the results. You just hit visualize, and right now all the buttons are completely blocked, and this is by choice, simply because we don't want you to be changing anything while the simulation is running. And this idea is again originating from the fact that we don't want you to be changing things by mistake while a simulation is running, because the solvers that we have used, they are completely capable of picking up the results. So if a simulation is running and at the same time you basically hit run, it is going to you change some value, it will immediately pick up the new value and it will start working from there. So we don't want that. Okay, so the simulation is still running. I'll close the software for now and launch it again. Just give me, let's see what we have in between. Yeah, it's still running in the background. Okay, I don't want this to basically continue. I'll kill it for now, if that's possible at all. Okay, yeah, launch it again. Yeah, so these simulations take time and they also can be heavy at times, so we don't want to do everything real time right now. Okay, so that basically wraps up macro scale modeling. On the micro scale modeling, on the Monte Carlo side of things, we again have the same philosophy. We have loaded up some alloys for you, but at the same time we have the same thing about scan patterns. So you can upload the scan pattern, and the software will automatically pick up that scan pattern, and then based on the melting temperature, thermal diffusivity, conductivity, preheat temperature, laser scanning speed, and many other process parameters, it will be able to set up a simulation for you and run the laser accordingly. Now on the computation settings front, this is slightly different from what we do in CFD. We have something called the number of random spins that you want to assign to your particular alloy before the laser starts running over it. And then there are two things called simple cube 26N and simple cube N 6N. So we are going for the most advanced one called simple cube 26N, and this means that for each grain the neighboring 20, so a cube actually has 26 neighbors, okay, and those 26 neighbors, you will arrive at that number if you also take the neighbors whose edges are touching, right. So you have 26 neighbors, and based on any changes that happen in these 26 neighbors, it will affect the grain size and its orientation of the primary cube or the primary grain sitting in between. Again, the same philosophy with accuracy and performance, data saving frequency, and all our solvers are completely parallel. So we can just change the number here, and it doesn't have to be a global number. So if you think that microstructure modeling is taking more simulation time, that you can go with higher number of cores here, and with macro scale, if you think it's taking less time, you can go with less number of cores here. You can even go in serial processing. You can just give one, it will still work, right? So if we hit save, now it's giving error again because we have not uploaded the scan pattern. So let me upload the scan pattern from one of the demos here. Yeah, and then we hit save. It didn't complain because now we have a scan pattern. I won't run solver for this one because it's just going to take time, and with so much video and live streaming going on, it may not be a good idea. But nevertheless, we have some results for one layer micro scale. You can see we have some, yeah, right. So it's one layer and two tracks. You can see as the laser runs over this microstructures, the grain sizes are changing. I'll play it one more time. Right, so this is what we can do with this type of modeling. And then lastly, we have deep learning module where you can give like an agent name called, for example, demo AI agent 1, right, and the number of neurons per layer. So like I said, it's a deep learning module, and the number of neurons per layer basically explains or indicates the complexity of how complex your neural network has to be, or your deep learning module has to be, right. So if you give a number 4, it will be less complex, but we have found 8 is a good number in most of the cases. Now what we did, let me explain how exactly you can use some of this data. Okay, so let's look at some of the NIST data. They have power, welding speed, gas flow rate, focal position, angular position, material thickness, weld number and cross section, position in the weld, and they have this different sets of process parameters for 246 experiments, right. And corresponding to each of these experiments, they have reported the weld seam width for the copper. Okay, so there was I think lab joint sort of welding that they did, and then we have corresponding 246 values for the weld width. Now, this is a lot of good data, and I mean, I have no idea why this won't be used for making any future predictions about similar processes. Right? So what we can do, we just upload the input data, the process parameters. Okay, so let me see if I can go to this one. Okay, and then we also upload the values that are relevant to that basically come out of this experiment, and then we train new AI. So the name of the agent is demo AI agent 1. You can see that the model is learning from this data, right? And I've let it run because it's relatively quick. So it takes 10, it's going to run up to 10,000 iterations, and we are already at 1,500. It may take another minute or so. You can see, for those of you who are from this AI background, we can also maximize this screen and minimize this terminal basically to see things in more detail. You can see that the loss or the error is decreasing gradually as the AI module is making correlations between the process parameters and the corresponding weld width. You can see that the user interface also indicates the last button that you had pressed. So it's currently running this train new AI solver in the background, and that's why this button is highlighted. So you don't get lost basically which was the last button that you hit. So initially the errors were, I think, around 200, and now they are reduced to 177, and after a while they will tend to become steady. They won't. And perhaps if you increase the number of layers or number of neurons per layer from 8 to maybe 16 or 32, the training will happen slowly, but it is likely it may give better results. But of course you need to do that sort of tweaking and calibrations before you can come to a good number. Okay, almost there, 9,000 iterations. Okay, so it stopped before 10,000 because we have implemented a thing called early stopping. That means if there is no further improvement, or in fact if there is a increase in error, again it will stop the training and take the best results that are available up to that point. It's saying AI training completed. Now you can load your trained model, which was what was it, live webinar 2 maybe. So your model should be saved in this demo AI agent 1. Your model is loaded, and now we will load some data that this trained AI model has never seen before. It's going to be the set of process parameters, different values for the same set of process parameters, and then we hit predict, and it will predict some numbers. So we provided one value, and it is predicting 321.173 for that set of process parameters. And then, I mean, of course you can have different set of process parameters, and it will predict different values. Right, so this in nutshell is a quick run through of the software, and of course there might be a lot of we know there's a lot of scope for adding solvers and improving the existing solvers, but this is where we stand as of now. And we have already started installing AM PravaH at some of the IITs, and we are very happy that the students are already started producing some results using this. Okay, so why AM PravaH? I mean, I'm not aware of many CFD software that cater specifically to additive manufacturing industry, at least to this amount of exclusivity and this inclusivity. And I mean, we call it an all-inclusive software because we are trying to not just focus on the computational modeling aspect, but we are trying to really make the computational modeling end-to-end process for the user. right? So there are basically 4 aspects that everyone cares about when deciding to go for the software. The first one, of course, and the most important, is accuracy. Everything else is secondary. So like I mentioned, AM PravaH is truly N-phase. It can take inert air, solid, melted solid, and also advanced vapor phase if necessary. Users can assign exact chamber conditions and thermophysical properties for the alloys and the inert gas, exact fluid dynamics, thermodynamics, mass conservation, laser dynamics, phase change, physics equations are included. We have a dedicated Monte Carlo simulator for grains morphology, growth and misorientation. We have a dedicated discrete element method for particle dynamics. Users can use detailed custom tracks for multiple layers and custom powder size distributions. And we have also a dedicated VNV manual which is growing every day basically. Now, if I look at some of the other software that I am aware of to the best of my knowledge, they are mostly limited to single phase or maximum 2 phase modeling, ignoring the effects from other phases, and I don't think that's accurate. There's limited flexibility with assigning exact chamber conditions and thermophysical properties. Then there are certain types of assumptions that are made in solving the physics equations. Solvers are not available for microstructure analysis at all, keeping the whole computational modeling incomplete. On the performance side of things, again, AM PravaH has a lot of benefits. All the solvers are completely CPU parallelized for fast simulation runtimes. The post processor is actually, it also takes advantage of the, if you have good NVIDIA GPU cards, it will automatically pick up those and it will give you good results. This advanced deep learning modules, which is parallelized on GPUs, and this can enhance the experience of AM experimentalists and researchers. It has a simple, flattened modern interface for maximum performance. The terminal is decoupled from the post processor and in the user interface, again to improve the performance. It has multi-layer modeling, and it is very simple to launch. You just upload the Excel sheet of whatever you have, whatever strategy you have, and it will automatically pick up. And it has absolutely state-of-the-art visualization that benefits from latest GPU processors. Now, other software, scaling is possible, and I would say they are also parallelized on CPUs. But again, I mean, there's limited scaling because the licensing is dependent on how many processors you want to run. We don't do anything like that. If you have a 1000 core machine, you can take our software for the same price and you can run it on 1000 cores. So it actually launches our users in the domain of high performance computing. Utilization of experimental data is completely ignored. The user interfaces are very heavy and they slow down the computers. Okay. Another quick note on terms of performance, we are also testing this AM PravaH on some of the AMD processors, and we have found that AM PravaH tends to give good results on AMD processors as well, and not just the Intel processors. Now, coming to the third aspect, which is cost. Licenses are not limited by processor count irrespective of the license type. I think this is the biggest cost saving gesture that we are offering to the users. Users can truly operate in the realm of high performance computing and low cost. Okay, this is developed in an economical manner, utilizing and improvising the research of developers around the globe and the developers at Paanduv. There are no costs involved for bug fixes, upgrades, updates and maintenance. Now, when we look at other software, this is the most challenging aspect. Costs are very high for, and especially if you want to go with good core count, the costs they multiply many times. The financial costs make it difficult for AM modeling to reach academia and industry, especially in growing economies, and costs keep accumulating for any changes. If you want to change anything in the original version of the license, the costs will increase for you. In terms of support, this is again the fourth pillar of what our philosophy towards developing AM PravaH is the development team is easily accessible for custom software changes and upgrades. There are both on-site and virtual support possible if it is realistic. There is no intermediate layer of sales engineers and resellers and support engineers. If you have a problem, you will be put directly in contact with one of the scientists here, and he will directly try to fix your problem. If there's something off with the code, he will try to fix that, and within 60 days, if you have a quick support question, he will answer you within a couple of hours. There's a dedicated onboarding which is free of cost. There is dedicated support hours per year which are free of cost. Bug fixes within a fixed amount of time, they will go directly to a developer like I mentioned. custom development is totally possible. I mean, this is something which is very, very powerful. If you have something in your mind, if you're doing some special type of additive manufacturing process which is not currently offered in terms of simulations by the market, then we can develop something for you and give it to you, right? Because we have complete control on the source code. The ownership of the company is very clear. I mean, we are all scientists and developers here. There's a clear philosophy of promoting the tech growth of the world in a sustainable manner, and we are not purely motivated by financial matters when we have developed this software. When we talk about other software, developers are not easily accessible due to hierarchical company structures. You will have to navigate through a thick layer of support and sales engineers before you can actually have your problem addressed. The support hours are very free. That too, they are offered by non-developers. Bug fixes are not simple or simply not possible. Custom development not easy or not possible. These are completely black box solvers, and that makes them unsuitable for research. Company ownerships and motives can be unclear as well sometimes, right? So some of the licensing details, like I mentioned, there's unlimited core process count, no matter whether you get an academic license, industrial license, for how many years you want it. We are going to keep the unlimited core count. The support is dedicated. We have hands-on onboarding, bug fixes, important patch and version updates, and we have both long-term and perpetual licenses as well for both academia and industry. And for academia, the prices are severely discounted compared to industry, so that we have taken care as well. A quick note before summing up the presentation about Paanduv. So we are a team of CFD developers and not really many application engineers here, mostly scientists and developers, and we basically operate in the technologies such as computational fluid dynamics, artificial intelligence, and other than 3D printing, we are also into water, environmental, aerospace, energy, defense, microfluidics, consumer products, automotive, thermo machinery, and HVAC industries. And our business philosophy is very simple. Anything related to technology, especially computational modeling or AI side of things, we are into that. So this is our website, www.paanduvapplications.com, and I hope you will get a lot of information and complete idea of what exactly we do. But our main work is CFD consultation, CFD development, CFD marketplace, CFD academic program, coupling AI and CFD, and we also help local starters or users of CFD in deciding the computer hardware for their organizations. So yeah, there are multiple means of contacting us, but the best one is to write an email to support@paanduv.com. One of us will get back to you in a short span of time. We are also on LinkedIn, and there's a dedicated page available on our website as well. And we are located in India, in the northern part of India, and yeah, that's basically it from our end, from my end in this case. So thank you very much, and we will be happy to take any questions. Yeah, so one question is, how long can simulations take? Depends on the accuracy and the performance parameter again, but most of the work that we have shown today is a matter of few hours actually. And again, if you really jack up the accuracy, and if you want to really go with a fine mesh, it can take overnight on maybe a day or two as well, right? No, this is not currently coupled with the thermal fluid model of OpenFOAM. This is completely separate. For the thermal mechanical model, we are going to incorporate a different solver altogether. Okay. If you have any more questions, again you can send your queries to support@paanduv.com. But that's it for now, and see you again, guys.